Most equipment is rated on a symmetrical basis. And that just means that you have a short circuit. This is the time axis going this way. And most current is rated just on a symmetrical basis. That's the way most devices are rated today. It wasn't always that way, you know, decades ago. But what happens is when a short circuit actually occurs, there's a DC component that gets superimposed on here. So this symmetrical short circuit current actually is superimposed on top of this exponentially decaying DC component. So it does something like this. Now, where that DC component comes from, I mean, you might have heard of it before, but where it actually comes from is when you have a circuit, and a circuit is under normal conditions, just serving normal load current and everything, and somewhere out of nowhere a short circuit occurs. The circuit itself, the conductors, the transformers, everything that makes up the circuit is highly inductive. The load's not. The load's mostly resistive. But the circuit is extremely inductive. And so all of a sudden you have this current going from a smaller load current and trying to make a step change to a really high short circuit current. Current doesn't change instantaneously through inductance. And so what happens is you get this DC component as a direct result of the X over R ratio, and everything gets offset. On the left, if you have an ungrounded, let's say we have a delta system, an ungrounded delta system on the left, you see phase A, phase B, and phase C. Those are the voltages, and you have phase-to-phase voltage from A to B, B to C, and C back to A. And there's actually a 0 volt reference that kind of passes through the middle of all that. It doesn't normally get acknowledged or anything, but it's there. But what happens if you have an ungrounded system, an ungrounded delta, and let's say a short circuit occurs? Let's say a short circuit occurs on the B phase, for example. Then what's going to happen is the voltage on the B phase goes to 0, and the A and the C phases elevate. They go up. So you have the B phase voltage going to 0, and then you have the A phase and the C phase voltage actually going up. And it's like, wait a minute, if it goes up, is that a problem? Yes and no. There's a good answer. Yes and no. It depends on how the system was designed. So a true ungrounded delta is actually, if it's properly designed, is designed for continuous operation. But what happens is when you have a fault on, let's say, like the B phase, yes, it goes to 0, but you still have full phase-to-phase voltage among all the phases. So you still have the complete phase-to-phase voltage from A to C. And when the A and the C elevated went up, you still have the full voltage from C to B and the full voltage from A to B. The problem is that the voltage from C to B and A to B, yes, it's the magnitude of the phase to phase, but it's connected phase to ground. The thing about the digital relays is it was an evolution for digital relays. What we had before the digital relays were the electromechanical relays. The way that these work, and the reason these were here forever, because they're so easy to use, is there were only a couple of settings on them. And so the settings, let me explain the settings. I already talked about the one. Let me see if I can get a decent view of it. The first setting is the one that's up here, the amp tap setting across here. And you take this plug. Let me do it this way. You take this plug, this thing right here, and that gets plugged in to one of the holes. And what that does is that completes one of the circuits that goes to the coil down here that defines how much current it takes for this disc to begin to rotate. And this disc in here is much like the disc in the old school analog watt-hour meters that would spin around. In fact, this coil back here, right back here, it's kind of a C-shaped. It comes around, it's kind of hard to see, but it comes around and it goes around this induction disc in here. So when the current exceeds the amp tap setting, then this disc is going to begin to rotate. And when this disc begins to rotate, what happens, you can see there's a horizontal shaft that goes up through here. do it this way. There's a horizontal shaft that goes up through here. And on that shaft, there's a secondary disc right here. And that secondary disc, it's kind of hard to see, but back here, there's a wee little, see if I can get it from the back. There's a wee little post right here. And that little post starts to rotate. The disc spins around, the secondary disc spins around, that little post comes around, and what it's going to do, there's a contact right there. And it'll push on that contact and close it. And then when that happens, this coil right here energizes, and there's a little contact here. And this little contact pulls.